What if I told you that everything you believed about the construction of the pyramids is outdated? Modern engineers with their cranes and hydraulics look at these ancient stones with bewilderment, unable to comprehend how such a feat was possible. We are used to thinking that moving multi-ton loads requires roaring engines, steel cables, and complex fuels. The ancient Egyptians, however, looked at physics differently, turning gravity and sand themselves into their allies. They moved blocks weighing 10 tons faster than a modern crew can set up a construction site. This seems impossible if we measure their achievements by today's standards of efficiency and technology. But they had something we don't have: a complete understanding of simple natural forces and the ability to use them with frightening efficiency. They didn't fight against the weight of the stone, but made it work for them, using cunning instead of brute force. The history we were taught in school omits the most important details hidden in engineering calculations. Forget the myths about millions of slaves simply pulling ropes under the lashes of whips. The reality was much more complex, interesting, and, if you will, technological, but in a completely different sense of the word. It was a triumph of mind over matter, a calculation that left no room for error. Watch the video to the end, and you will learn how water and sand replaced the most powerful modern mechanisms for ancient builders. Are you ready to learn the truth about the real scale of this task? When you stand next to a 2.5-ton block of limestone, you feel your physical insignificance. Imagine a modern SUV compressed into a dense stone cube that needs to be not just moved, but transported for miles. Now imagine that there are not 10 or 100 such cubes, but more than 2 million. You might think that the main problem was the weight, but that's not quite true. Weight only becomes a problem when you try to lift it vertically with brute force. Egyptian engineers quickly realized that fighting gravity head-on was a recipe for failure and a waste of resources. They changed their approach to the concept of weight, turning static weight into dynamic movement. The biggest mystery for researchers for a long time was the speed at which these giant blocks were laid. Mathematical calculations show that in order to complete the Great Pyramid on time, one block had to be laid every 2 to 3 minutes. This is an incredible pace even for a modern construction site equipped with tower cranes. This meant that the transportation process did not stop for a second, working like a perfect conveyor belt. To achieve such speed, a perfectly flat road surface was required, which had to be created in desert conditions. Any unevenness, hole, or stone in the path of the skids could stop the movement of a multi-ton block. Engineers put a tremendous amount of effort into preparing tracks that were harder than modern asphalt. They used compacted crushed stone and special mortars to create the perfect highway for the stone. We often forget that stone is a very fragile material, despite its hardness and weight. If such a block is dropped or hit during transport, it can split, and months of work will go to waste.
If we pull too fast,
Therefore, movement had to be not only fast, but also incredibly smooth, avoiding sharp impacts. This required the coordinated actions of dozens of people working as a single organism. Interestingly, the granite blocks used to cover the king's chamber weighed not 2, but up to 80 tons. Moving such a colossus required completely different engineering solutions and a different degree of responsibility. One mistake could have led to a catastrophe that would have been impossible to fix. These blocks required special roads, special sleds, and elite teams of transporters. Do you think the people of that time could have possessed knowledge that we have simply forgotten how to apply today? Or are we overestimating the complexity of the task and underestimating the capabilities of human perseverance? I am very interested to hear your point of view. What do you think about the capabilities of ancient engineers?
to the right, gently now. Lock it in.
Guess how long it would have taken to build this if there had been no river. The Nile was not only a source of water and life for ancient civilization, but also a major transport artery. Without this river, the construction of the pyramids would have taken thousands of years, making the project economically unfeasible. The Egyptians were masters of hydraulic engineering, skilled at harnessing water flows for their own purposes. The limestone quarries were relatively close by, but the granite was mined in Aswan, hundreds of kilometers from the Giza Plateau. Transporting such huge blocks overland would have been madness, depleting the country's resources in a matter of months. Therefore, engineers developed a complex logistics system based on the seasonal floods of the Great River. They waited for the moment when the water rose as high as possible to reduce the distance over land. Special barges were built to transport the stones, whose carrying capacity is still impressive today. These vessels were assembled from Lebanese cedar without using a single metal nail, only a system of grooves and ropes. They could carry loads of hundreds of tons, gliding through the water with majestic slowness. Steering such a vessel required knowledge of currents, winds, and the characteristics of the fairway. A special skill was required to load a multi-ton block onto a wooden vessel that could capsize. For this purpose, special bulk piers were built.
We have it, steady. Good, hold it there.
The barge was brought under the load or loaded with ballast to level it with the shore. It was a delicate operation, where the risk of losing the stone and the ship was maximum. The Egyptians dug artificial canals that came as close as possible to the pyramid construction sites. They literally changed the landscape, bringing water to where it was needed to unload materials. The port was located at the very foot of the plateau, turning the desert into a bustling harbor. Archaeologists find the remains of these colossal hydraulic structures. But as soon as the stone was on the shore, completely different laws of physics came into play. The water had done its job by delivering the cargo, but now it had to be dragged across the sand. In the next chapter, you will learn how one simple trick changed the rules of the game.
Keep the pace steady. Pull together now.
I discovered this by accident while studying old frescoes that no one paid any attention to. In the tomb of the nobleman Yehuti Ketep, hundreds of people are pulling a sled, and one man is standing at the very front of the runners, pouring something from a jug onto them. For a long time, historians considered this to be a simple ritual act, an offering to the gods or a symbol of purification of the path. However, physicists decided to test this detail in practice and were amazed by the result. It turned out that the man in the fresco is pouring ordinary water, and this is a key element of the technology. Dry desert sand behaves treacherously. It accumulates in front of the runners, creating a barrier that slows down movement. The harder you pull, the higher this sand barrier becomes. Adding the right amount of water radically changes the physical properties of the sand. Water creates capillary bridges between the grains of sand, binding them together and turning the loose mass into a solid surface. The sand stops scattering and becomes similar to a solid dirt road. The runners of the sled stop digging in and begin to slide over the surface. Experiments have shown that friction is reduced by almost half. This means that half as many people are needed to move the same stone block, whereas previously 100 workers were needed to move a statue. With water, 50 were enough. This is a huge saving in human resources and energy. But there was an important nuance here. There had to be a strictly defined amount of water. If too little was poured, the sand would remain dry and loose, and there would be no effect. If too much was poured and the sand turned into mud, the sled would get stuck even more. An experienced master was needed who could sense the condition of the soil and measure out the moisture. This jug operator was not just a water carrier, but the most important specialist in the team. The speed of the entire procession and the fatigue of the pullers depended on his actions. He had to pour water evenly, directly under the approaching runners. This required coordination and precise calculation of the speed of movement. So, the block slides along the wet sand, but ahead of it lies a climb to a great height. There is no more flat road. The path to the sky begins. Don't forget to like this if you are surprised by the simplicity of this solution. Are you ready for the shocking truth about how stones were lifted to a height of 140 meters? The question of ramps remains the most controversial in Egyptology, as there is almost no direct archaeological evidence left.
All together now.
A straight ramp to the top of the pyramid
not
would have
stop
required
until
as
the block
much
is
material
set.
as was used to build the pyramid itself.
Together now.
Ancient engineers had to come up with a system that grew along with the building. One of the most elegant theories is the use of a spiral ramp winding around the outside of the pyramid. Such a road would rest on the blocks themselves without requiring enormous amounts of sand and gravel for the embankment. It is similar to a mountain serpentine road that trucks use to climb a hill. But an external spiral ramp has its drawbacks, the main one being the difficulty of controlling the angles of the pyramid. If the entire structure is covered by embankments, surveyors cannot check whether the construction is proceeding evenly. And the accuracy of the Great Pyramid is astonishing even today, with an error of only a fraction of a degree. This means that the angles had to remain open for sighting. There is a theory of an internal ramp hidden inside the pyramid's masonry. French architect Jean-Pierre Houdin proposed a model in which blocks were lifted through tunnels inside the pyramid. This explains why we do not find the remains of giant embankments around the plateau. Infrared scanning shows spiral density anomalies, which indirectly confirms this assumption. The ramps most likely had a complex structure with reinforced sides and wooden decking. Simply piling up sand was not enough, as it would have crumbled under the weight of multi-ton sleds. A rigid structure was needed that could withstand the intense traffic of heavy loads. Perhaps beams were built into the body of the ramp for workers to rest their feet on. The angle of such a ramp could not exceed 7 to 8 degrees. With a steeper incline, people would simply not have enough traction with the surface to pull the load. Physics dictated strict limitations on the geometry of the construction site. Each degree of incline increased the required traction force many times over. The stones were lifted higher and higher, but they still had to be cut with incredible precision. How did the Egyptians cut the hardest granite without diamond saws and lasers? In the next chapter, you will learn about cutting techniques that seem primitive but produced perfect results. We often imagine ancient tools as crude and ineffective. However, Egyptian craftsmen achieved the pinnacle of stone processing with only copper, stone, and wood at their disposal. They did not have iron, and copper is a soft metal that quickly dulls against hard granite. Quartz sand or corundum grit served as an abrasive, which was sprinkled under the copper blade. In this case, copper acted only as a guide, as a holder for the abrasive. It was the hard crystals of sand that dug into the granite, millimeter by millimeter, wearing away the rock. It was not a process of cutting. The saws were huge, two-handed, and required the coordinated work of two craftsmen. They moved the blade rhythmically, creating a characteristic sound that echoed throughout the quarry. The weight of the saw itself helped to create the necessary pressure on the abrasive. Periodically, the craftsmen added water and fresh sand. The speed of such cutting was incredibly slow by modern standards, a few millimeters per hour, but the Egyptians had an advantage that we do not have, a huge amount of time and cheap labor. They could put dozens of sawyers on one block, working in 3 shifts. Tubular copper drills, which worked on the same principle, were used to drill holes. A bow and arrow rotated the tube, and sand gnawed a ring groove in the stone. Archaeologists find granite cores, cylinders left inside after drilling. Wooden wedges were used to split huge rocks. A series of holes were cut along the line of the future fracture. Dry wood was hammered into them, and water was poured over them. The wood swelled, creating enormous pressure from inside the stone. The rock cracked exactly along the planned line, without unnecessary noise and dust. These simple methods produced results that we can still see thousands of years later. Perfect edges, tight joints, smooth surfaces. All this is the fruit of human patience and sand. What if I showed you a time machine that would take us to a construction site where blocks float upwards? If the block is sealed to the shaft or a wooden float is used, the water can lift the load upward. This is the principle of locks, which is used today in shipping canals around the world. Water has enormous potential energy, and the Egyptians knew how to control it. Imagine a vertical well inside the pyramid filled with water. A stone is tied to a wooden raft, and as the water level rises, the load floats up. This would solve the problem of delivering blocks to the upper tiers without giant ramps. However, such a system would require perfect waterproofing of the chambers and shafts. The Egyptians used gypsum and special mortars, but it is extremely difficult to hold a column of water of such height. Critics of this theory point to the absence of traces of water erosion in the shafts of the pyramids. A more down-to-earth version of the elevator is a system of levers and tilting beams. The Shadi CF, a device for lifting water from a river, has been known to the Egyptians since ancient times. The same principle of a lever with a counterweight could have been used to lift stones. On the short arm of the lever was a heavy stone, and on the long arm was a basket with a load or a team of workers. Such devices allowed blocks to be lifted step by step, from ledge to ledge. It would be like passing a bucket of water along a chain during a fire. Only instead of a bucket, there was a 2-ton block. Such a system is compact and does not require the construction of the external embankments. It could be mounted directly on the facade of the pyramid under construction. The counterweights could be bags of sand or stones, which were easy to fill and empty. The workers did not need to pull the weight up. They only needed to pull the rope down using their own weight. This is physiologically much more convenient and effective than lifting heavy weights. Traces of the use of such mechanisms are found in later buildings. Holes in stones, which could have served as sockets for wooden beams, are often found. The wood rotted away thousands of years ago, but the engineering signature remained in the stone. Mechanics versus brute force. That was the motto of Egyptian engineers. But even the most ingenious mechanisms are useless without the skill to apply them.
Mechanics over brute force. Steady now.
The museums of Cairo house a strange wooden object that resembles a curved cradle. For a long time, its purpose remained a mystery until engineers figured out its function. This device turned a square block into something like a wheel. By attaching such wooden segments to the sides of the stone, builders were able to roll it instead of dragging it. Rolling friction is always less than sliding friction. This is a law of physics. It is much easier to roll a cylinder than to drag a cube along the ground. 4 such wooden segments tied around the block turned it into a barrel. This solution is ingenious in its simplicity and effectiveness for certain sections of the route. There was no need to lubricate the road or pour water. It was enough to simply push. In addition, the wood protected the stone itself from chips and damage during transportation. The block arrived at the installation site in perfect condition. This method also made it easy to turn the block in place. Unlike sleds, which have a large turning radius, a rounded stone can be turned any way you want. This was critically important in the cramped conditions of laying the last rows of masonry. The maneuverability of the load increased significantly. However, this method had its limitations. It was not suitable for all block shapes. It was impossible to roll huge rectangular floor beams in this way. But for standard limestone blocks, which make up 90% of the pyramid, it was the ideal solution. Wood was in short supply in Egypt, so these cradles were carefully preserved and repaired. They were made of sturdy acacia or imported cedar, which could withstand the weight of the stone. The wear and tear on the wood was significant, but the savings in labor costs made up for the expense. Engineering was involved at all levels, from extraction to laying. But who were the people who operated these tools? Were they downtrodden slaves or highly skilled professionals? The myth that the pyramids were built by slaves under the lash of whips was invented by Greek historians much later. Archaeological excavations of the builders' settlement in Giza have overturned our understanding of the social structure of that era. These were not prison barracks, but a full-fledged city with normal houses, bakeries, and hospitals. The people who worked here ate meat, drank beer, and received medical care. Analysis of the workers' bones showed signs of successfully healed fractures and even amputations. This means that professional doctors took care of the builders' health, and the state paid for their treatment. A slave who broke his leg would simply be thrown out, but a skilled stonemason would be treated and returned to work. This was a rational approach to valuable personnel. The workers were organized into brigades or filas, each of which had its own name and pride. Graffiti is often found on the blocks. Friends of Khufu, drunks of Menkore. This is reminiscent of the modern names of sports teams or construction crews. There was competition between the brigades. Whoever laid more blocks would receive more rewards. They were paid in food, cloth, and oil. It was a reliable government job that guaranteed stability for the workers' entire family. During the Nile flood season, when fieldwork was impossible, the peasants went to work on construction sites. It was a kind of tax labor, but with full provisions. The builders' diet was surprisingly high in calories and protein. Huge slaughterhouses supplied thousands of head of cattle to feed this army. Bread, onions, garlic, and fish complemented the menu, providing energy for hard physical labor. The state spent enormous resources on food logistics. The families of the craftsmen also lived in the builders' town, where the women baked bread and mended clothes. This was not a temporary camp, but a permanent settlement that existed for decades. People who had dedicated their lives to one great goal were born and died here.
Here, eat this.
Thus, the secret to the speed of construction was not fear of punishment, but competent organization and motivation. A well-fed and motivated professional works faster and better than a dozen hungry slaves.
This block is sound, despite the minor fissure. It will fit perfectly.
The Egyptians were not only engineers, but also excellent geologists. They understood the structure of stone, its layers and hidden defects. The choice of location for the pyramid was not accidental. The Giza Plateau is a solid limestone base capable of supporting millions of tons of weight. Building such a structure on sand would have been suicidal.
Pull harder, men.
The blocks were not simply stacked on top of each other, but were arranged according to their individual shapes. This is known as polygonal or quadrangular masonry, where each stone occupies its own unique place. The joints between the blocks and the facing were so thin that it was impossible to insert a knife blade between them. This required fitting directly at the installation site. A gypsum-based mortar was used to bind the blocks together, which acted as a lubricant. While the mortar was still liquid, the massive stone could be moved slightly to adjust its position. When the gypsum hardened, it became solid but elastic, allowing the building to breathe during temperature changes. The internal chambers and corridors are oriented with astronomical precision. The entrance to the pyramid faces strictly north, with an error of only a few fractions of a degree. This suggests that the engineers used the starry sky as a giant measuring instrument. The granite for the interior decoration was transported thousands of kilometers, selecting only the best veins. They knew that limestone was soft and unreliable for the ceilings of the chambers, where the pressure was enormous.
Look at that.
Granite beams distributed the load.
Perfect. The king will be pleased with our work today.
The floors in the temples around the pyramids are laid with slabs of basalt, a black, incredibly hard stone. Cutting and fitting it required even more effort than working with granite.
Indeed.
Nevertheless, the floors are still perfectly flat. The builders even took possible earthquakes into account. The pyramid's design, with its wide base and tapering shape, is the most earthquake-resistant form of building. The blocks are held in place by their own weight, and when shaken, they only settle more firmly into place.
Pull together, lift the stone. Steady on the ropes there, move it
The
up.
main machine that built the pyramids was not cranes or levitation, but Egyptian society itself. It was a social technology that allowed tens of thousands of people to unite their efforts for a single purpose. The ability to coordinate the actions of huge masses of people is the real miracle of that era. Imagine the logistical challenge: feeding, watering, and providing tools for the population of a small city every day. Deliveries of stone, the movement of barges, and the work of smithies and bakeries all had to be synchronized. This required a level of management comparable to that of modern corporations. Scribe were the nervous system of this machine. They recorded everything: production rates, grain consumption, the number of sick people. The document flow was enormous, and thanks to the papyri that have been found, we even know the names of the foremen. It was bureaucracy in the best sense of the word, a system of accounting and control. The hierarchy was strict but transparent. Everyone knew their place in their task. From a simple porter to the chief architect, everyone was a cog in a single mechanism. A failure in one link could stop the entire construction, so discipline was ironclad. This social machine worked without weekends or holidays as we understand them. Shifts followed one another, and work continued from dawn to dusk. Nighttime was used to prepare tools and take measurements. We often look for secret technologies in mechanics, forgetting about management technologies. The ability to mobilize the resources of an entire country without collapsing the economy is the art of state management. The pyramids are a monument not only to engineering, but also to administration. With the end of the era of the Great Pyramids, this social machine did not disappear, but transformed. The experience of large-scale construction projects was useful in the creation of irrigation systems and temples. Organizational skills became part of the cultural code.
Together now, lift!
We have dismantled the myth that it was impossible to build pyramids with primitive tools. It turns out that primitive tools in the hands of ingenious organizers and observant physicists can work wonders. Water, sand, levers, and human labor are the components of this success. The Egyptians did not defeat nature, they cooperated with it, using its laws. Their methods were elegant, economical, and frighteningly effective. They showed us that limitations exist only in our minds. A 10-ton block is not heavy if you know how to turn friction into sliding. The history of ancient Egypt is not about aliens. Which of these ancient engineering solutions did you find most surprising? Was it the trick with water or the use of stone cradles? Share your opinion in the comments and be sure to subscribe to the channel so you don't miss new analyses of historical mysteries.